Alright, so in this video we're going to talk a little bit about uniform circular motion. So for my example that we're going to look at here, we have a planet orbiting around a star. And we're saying uniform circular motion, so even though this isn't perfectly drawn, this is a circle. So the r value here, 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 etc. would be the same. And we want to discuss the acceleration that this planet here is experiencing due to the star here. Alright, so first let's examine the velocity, because to get to acceleration off, it's a good idea to go through velocity. So we can analyze the velocity to understand what's happening with the acceleration. So we know that velocity is equal to displacement over time. So the path that the object takes in this case is a circle, so I can put displacement, I could put 2 pi r, which is the formula for the circumference of a circle. And it's going to make one circumference in something we refer to as the period. So we use a capital T for that, and this is the time to orbit once. Alright, so we have some information hidden in here now. And we think about the time to orbit once. The time is the same. We don't have on Earth, the orbital period would be 365.25 days. Now we handle that 0.25 days through a leap year, but that's just a human way of accounting. It still takes the same amount of time each year to go around the sun. It isn't 200 days some years and 400 another year. It is the same amount of time. So the orbital period is going to be fixed, and r, we said this is a circle, so that's also fixed. So what we're saying here is that the magnitude of the velocity is constant. But remember, velocity is a vector and it has both a magnitude and a direction. So let's think about the direction. Now this orbital velocity I've just derived here, velocity equals 2 pi r over t, is often referred to as a tangential velocity, because it's the velocity vector would point tangent to the orbital path. So as the planet orbits around the star, you'll notice here that tangent to the orbital path, or tangent to the circle, the arrows don't point in the same direction. They change as the object orbits around the star. So the direction of the velocity changes. So that means we still have an acceleration. Because we have a change in velocity, it's just a change in direction rather than a change in the size of the velocity. And we're going to use two different vocabulary words to discuss those two different types of acceleration. So we're going to have tangential acceleration, and the tangential acceleration is going to cause the change in magnitude of the velocity. So in our scenario we've just drawn, the tangential acceleration would be 0. We're going to say the radial acceleration causes the change in direction. And radial acceleration is going to point towards the point of rotation. So as the object orbits around, the acceleration continues to point towards the point of rotation. And inward is defined as positive. So these would all be positive accelerations. If you have an acceleration that points directly out from the point of rotation, that would be considered a negative acceleration. I tend to write problems where the radial acceleration is positive, because I like to work a lot more with orbital dynamics because I'm also an astronomer. Alright, so now that we understand the concept and the vocabulary word a little bit better, let's move on and learn actually how to calculate the radial acceleration. Alright, so to start the derivation of the radial acceleration equation, we're going to do a little bit of a trick here. We're going to say r dot r. Remember, r is that position vector. It's sort of like a pointing vector in three-dimensional space. So we're saying, essentially establishing it as the radius of the orbit. And we're doing r dot r, so we're essentially dotting the same vector with itself, which means that they're parallel to each other already since it's the same vector. And so the dot product is just the vector squared, or the magnitude of the vector squared, so r squared. Alright, so remember we're trying to get from essentially position to acceleration. So in this process, we're going to take the derivative twice. So I'm going to take the derivative in terms of time of both sides. And since the dot product is a product or a multiplication, that means I need to use a product rule. And the derivative constant is 0 because we're just dealing with the magnitude and not the pointing vector anymore. So I'm just going to add those together since they're technically the same terms. And dr dt is the same thing as the velocity. And then I'm going to divide both sides by 2 and get rid of the 2. So we're going to be left with the original r vector dotted with the velocity vector. I'm now going to take the derivative again. I said we're going to take a second derivative because in order to get to acceleration, you need to take the derivative twice in terms of time and position vector. And once again, since they are dotted with each other, we are going to use a product rule. So we have dr dt dotted with v plus r times dv dt. Once again, dr dt is a velocity, so we end up with a velocity dotted with a velocity, plus we still have our r vector there, and dv dt is the same thing as acceleration. Alright, so we have to remember, since these are cross dot products, we have to deal with the dot product. So this is a velocity, this is the velocity. It's the same velocity, so they're automatically parallel to each other. So when you do the dot product, you just end up with velocity squared. And remember, with radial acceleration, it's acting along or towards or away from the point of rotation, which means that the radius is always going to be parallel to it. It may be parallel and may be anti-parallel, which is where you're going to get negative versus positive acceleration from. So we can reduce this down into just r times a, since those vectors are always going to be parallel or anti-parallel. And then we can rearrange the solve for acceleration. Technically speaking, this derivation would give you a negative sign, but remember, I made the original r in this direction, positive acceleration I defined is in this direction, so that's why you get that negative sign out, because technically in the way I derived it, we're dealing with an anti-parallel situation. So this is the equation in order to solve for radial acceleration. So it's going to equal to the velocity squared over the radius.